Good morning, this is Adam Wise of Andor Technology, an Oxford Instruments company. And in this short video I want to show you how cooling improves the sensitivity of a CCD, or more generally any camera. So the one that I have connected right now, the camera I have connected right now, is a Newton 920 BEX2DD. At the moment I have the cooling off, so there's a thermoelectric cooler in this camera, a multi-stage one, and right now it's set to off. I have a little cooling status window here to show that it's not doing anything right now. So the camera and the chip inside are somewhere close to room temperature. So I've got my acquisition here that I just took, and I have counts in it, much more than I would expect, because right now I've got the front of the camera completely light tight. So the counts that I'm seeing here, the values here, you can see the data point that I'm looking at, a few thousand counts. It's not generated by light, which is what I'd normally like to do, but it's generated by heat instead. So whether you call this thermal current, thermal counts, dark current, they are counts in the CCD that are not generated by light but by heat, and there's no way for the camera to determine whether that count came from light or heat. So as you can imagine, this causes a problem trying to measure a small signal. So not only are we losing a lot of our dynamic range, or some of our dynamic range, because we were already carrying a few extra thousand pointless counts, but the variance, both spatially across the sensor and temporally, or time-wise, that is to say measurement to measurement, the noise from that, the variance from that, is going to cause some problems if I'm trying to measure a small signal, because that small signal will be lost in the noise. So I need to cool this camera. I need to turn the thermoelectric cooling on before I'm going to do any kind of serious measurement. So I can show you the effect of that cooling if I open up the spec sheet here for the BEX2 CCD. That's this variant in the red line. So every time I cool by 20 degrees, I lose about 1.5 orders of magnitude of dark current. So dark current here in electrons per pixel per second, log scale, temperature in a linear scale. And you can see that the more that I cool, the better background I have, the quieter background I have. The first 20 degrees are the most important. We're going to lose something like 900,000 counts of dark current there. And then we squeeze more and more dark current out as we go deeper. It's a log scale, it's an Arrhenius process, so we're getting less and less of a jump each time, but we get a quieter background all the way down to -100. Of course, at that point, our expected value, our mean, and our variance for the dark current are all going to be much, much less than 1. So we should have, at small exposure times, a few seconds, should have essentially no dark current, which is going to be great for a very sensitive measurement. So to show you the effect of that cooling visually, I'm going to record a kinetic series, that is to say a movie measurement during the cooling process. So I'm going to set up a kinetic series. I'll go to Acquisition Setup. I've got 1 second so that the numbers are easy to compare to the spec sheet. I'm going to do 1 accumulation. I'm going to run for about 2 minutes because I don't intend to make you wait around that long. So I might not get to the ultimate cooling temperature, but I should get close. And that looks good. And I'm going to turn the cooling on, set it to -70, just whatever I can get to in a reasonable amount of time while this video plays, in your window. And then I'll start taking measurements. So to track it statistically, I'm going to open up a histogram. I can right-click on the plot window and show a data histogram. So I've got an ROI tracking right now, so you can see statistics updating here in the ROI. And you can see as the camera cools, and you can see the temperature reflected here, the histogram of dark counts, of dark current, is going to get dramatically shrunken towards 0. I'm going to have to zoom in a few times for you because it's going to go away, and collapse onto the left axis there. So this is a histogram of my counts. Across each value of possible counts, it's going to have the number of pixels that show up with that number of counts. And I'm going to zoom in and blow up the histogram again, blow up the distribution. So not only is it becoming lower, our mean value is collapsing towards 0, but there's still an analog offset applied before the ADC. But it's also going to become a tighter distribution. So our background will become not only lower, but more uniform, which is obviously very important. I'm going to zoom in again. And we're collapsing closer and closer to the offset. And I'll show you how to remove that offset with a bias frame in a separate video, so stay tuned for a video on bias frames. But for now, I just want to show the general trend. So we're only at -20. We've got a long way to go, and we've already eliminated the lion's share of our dark current. But I'm going to let this run for a few more degrees just to make sure that my point is made. Zoom in again. And it's going to continue shrinking towards the asymptotically towards the offset as time goes on. And I could wait around for the cooling to hit the ultimate level that I set. But for now, I think my point is made. So if you have any questions, feel free to contact me at a.wise@andor.com or visit the Andor website. And otherwise, have a good rest of your day.